Two people are booking the very last seat on a flight at the exact same millisecond. One in London, one in Tokyo. Both click confirm, both get a success message, but only one seat exists. So who gets the seat? Does the airline just double book it? The reason this usually doesn't go wrong comes down to 4 letters: A, C, I, D. First, what is a transaction? It's a group of database operations treated as a single unit of work. Take a bank transfer. Moving $500 from account A to account B at the database level, that's actually 2 operations. Now, what if the first one succeeds, but the server crashes before the second runs? Account A is down $500. Account B got nothing. The money just vanished. A transaction wraps both operations together. Either both happen or neither does. If anything goes wrong between begin and commit, the database rolls everything back, like it never happened. Oh, atomicity. The word atom means indivisible, and that's the idea. A transaction is all or nothing. Every operation inside it either fully completes or none of them do. There is no in-between. The database keeps a log of every change it's about to make. If the transaction fails halfway, it uses that write-ahead log to undo everything. Think of a vending machine, a complete exchange or no exchange. It never takes your money and gives you nothing. C. Consistency. A transaction can only move the database from one valid state to another. Every rule you've defined, constraints, foreign keys, data types, must hold true before the transaction and after it. Say the rule is, a balance can never go below 0. Deduct 500 from an account holding 300, and the result violates the rule, so the database rolls it back. Consistency is the one property that's partly your job. The database enforces the rules, but you define them. Isolation. Concurrent transactions should behave as if they ran one at a time, in sequence. Without it, you get a dirty read. Transaction B reads A's change before it commits, data that might get rolled back. Or a non-repeatable read. A reads a row, B updates and commits, and a reads the same row again to find a different value. Or a phantom read. A asks for all accounts over $1,000 and gets 5. B inserts 1, and now A's same query returns 6. Databases solve these with isolation levels, a dial that trades strictness for performance. Read uncommitted allows all 3 problems. Read committed stops dirty reads. Repeatable read also stops non-repeatable reads. And serializable stops all 3, but it's the slowest. Back to our airline seat, isolation is what stops 2 users booking it. The first transaction locks it, the second waits, then finds it gone. D. Durability. Once a transaction is committed, it stays committed even if the system crashes a millisecond later. The moment you get a success response, the data is on disk. Not in RAM, not in a buffer, on persistent storage. How? That write-ahead log again. Changes go to the log first. After a crash, the database replays the log and finishes the job. Think of a signed receipt. Once it's in your hand, the transaction is real. The store can't claim it never happened. Let's bring it back to the bank transfer and see how each property protected us. Atomicity. A crash mid-transfer rolled both operations back. No money lost. Consistency. The no negative balance rule was never violated. Isolation. Another transaction never saw the temporary, half-finished state. Durability. Once committed, the transfer was permanent, even if the database crashed right after. So what about NoSQL databases, like MongoDB, Cassandra, or DynamoDB? They don't always follow ACID. Many follow base instead. Basically available, soft state, and eventually consistent. Base trades strict correctness for speed and scale, which is fine for things like social feeds and recommendations. Acid is for when correctness is non-negotiable: money, medical, and legal records. And modern databases like Spanner and CockroachDB now do ACID at global scale.